start. So this is the GR session of the faculty student for this term. We will have 4 speakers today with a coffee break after the first 2 of them. And so our first speaker is Carlo, who's going to present us an axiomatic presentation of relativity.
Okay. Thank you. Good afternoon, everyone. Thank you all for coming. So this is my talk, an axiomatic presentation of special relativity. I really want to comment on the title because I had a hard time finding an appropriate title for this talk, because it's a rather philosophical motivation that's behind what I've done, and so I really didn't know what to write on the title. So I beg your pardon if there's any kind of misleading terms in the title. So in the first place, I want to tell you what got me thinking about this rigorous approach, or some fundamental approach to special relativity in the first place. So my first income of information, the first thing I had in mind was the ideas that my professor back in Spain told me last year when he presented the GR course with a rather not very typical perspective, which was revising special relativity from the beginning, which is a real, not the standard thing to do, but it was very appealing to me. And he told me there were some papers around Maskell, Wheeler, and Fletcher in which the basic ideas I'm going to tell you today are somewhat dealt with and somewhat introduced, but that are not completely organized and put together in a complete way so that there's a meaningful outcome in the end. So that's hopefully what I will do today. I will present you a successful outcome of a series of ponderings and thoughts that hopefully will let you grasp the basic idea of these developments, because obviously you don't have the time to go into the details. But I hope that you get the feeling that it is possible to formulate special relativity in a very intuitive and philosophically satisfying way. So, and finally, I will try to thank Karen and Pau, with your friends of mine, who helped me organize all these ideas in my mind. So, what's the motivation really for these talk? Because we all know special relativity. We know it works perfectly well. And so, why bother on the foundations of special relativity? But the first point is that there is lack of intuition and conceptual clarity at some levels when you study it from standard textbook presentations. And I'm not saying it's incomplete or mathematically insatisfactory, which is not. But I'm just saying that the physical principles that are behind the basic definitions of special relativity, or the basic mathematical objects of special relativity, are not completely clear, not completely explicit. So in very much the same way that you have Newton's laws in classical dynamics, you can see the direct correspondence between physical experience and mathematical principles. But in general, in special relativity, there's no such explicit link. Obviously, it must be somewhere, because at the end of the day, it's a successful physical theory, but it's not that explicit. So one of the good points or the good properties of this way of introducing special relativity is that it makes explicit all the physical principles that are needed. Another issue is that time and length need to be properly defined. You all know that we need a metric and a proper time and proper length, and all these notions are a bit confusing if you don't have a metric in the first place. So we require a proper definition for time and length without the metric, which is the basic object that we all use in special relativity. And in the end, I will present some ideas of mine that I actually thought about some weeks ago, and I want to just share with you. Maybe, I don't know, if you afterwards have any comment for further developments, I will be very happy to comment on them, and which are based and motivated by this exposition. So, what am I going to do today? So the first thing I will review special relativity very quickly. Then I talk about first principles and what is a satisfactory starting point, and because obviously I try to argue that the Minkowski metric by itself is not. Then we'll construct the space-time. I I will talk about plots and two fundamental principles that we need, that is the arrow of time, the principle of relativity. Then I will show that how roughly we recover special relativity, and usually roughly because we don't have the time to actually show all the details. And finally, I will show you this topic on your brain. So, special relativity. We all know and love the theory. We know it's a theory based on a four-dimensional fine space. We have a constant metric, which is the usual Minkowski product. That is when we use the usual normal coordinates, or orthonormal coordinates, if you like. We write the metric in this matrix expression, and we have the usual -1, 1, 1, 1, in the convention, 1, -1, 1, 1, the metric expression for this. So we know that from this basic object, we basically get all the physics. We get that, we define our free particles as being unitary time-like vectors, and then any inertial observer is constructed from a time-like vector is unitary, and so on and so forth. So we basically recover all the physics, or we ground all the physics on this object. So the question that I aim to assess here is why we use this object at all. Why is the Minkowski metric the natural object that we should use for special relativity? So let me go back to the first principle. So Lorentzian metric is going to go closer. What do I mean with this? What I mean is that Lorentzian metric is not an intuitive object that is tied to your everyday experience. Maybe if you're some kind of genius that can visualize 4 dimensions, probably you say that Minkowski metric is something intuitive, but for myself, Minkowski metric is not something entirely intuitive. And so there must be a non-trivial step or non-trivial gap between your intuition and your basic physical observations and Minkowski metric. So this talk is concerned with that gap, to showing an outline of a way of covering that gap in a mathematically consistent way. So this is really what I want to do. There's nothing else I really want to do. So don't expect more, don't expect less. This is what I want to show. So what is the starting point? So we want a kinetic theory. We just want to discuss kinematics at this stage. So the basic elements of the theory should be free particles in the first place, and then light, because we're concerned with relativistic phenomena, which, as you all know, are raised from considerations of electromagnetism, electromagnetic waves propagating, and the weird transformations laws that you needed to use to make Maxwell's equations covariant. So the first ingredient, of course, is light, and the second ingredient are free particles. So these are the two basic ingredients that we need for our theory. And so it's actually the starting point. So we need to think about these abstractly. We need to forget about what we normally think of light ray or of a particle as being, some kind of vector or a curve or something. You need to think at this stage abstractly about these things and just try to find a referent, a basic. You have to pin down the relations in between them from a previous theory that you know that's already satisfactory. And of course, this is Newton's classical dynamics and Maxwell's formulation of electromagnetism. So that's actually the starting point. So the point that you start the starting point for special relativity is actually Newtonian mechanics and Maxwell's equations formulated in that context. So what is this context? It's a three-dimensional, affine space-based field theory in which the dynamics are controlled by these equations and in which we find some funny behavior just from the theory of differential equations that those relations impose, that light has, that light propagates at a finite speed, and that speed actually controls the possibility of interaction between charged particles. And then, so, since we're only considering these forces at this stage, we can arguably say that light is the only extra ingredient of our theory, apart from matter. So, and this is a three-dimensional fine space formulation. So the natural thing to do is to say, okay, we have time, which is a universal parameter, it's just a real number, but we And we reduced to the isometry group of this 3 affine space with the Euclidean metric, which is the Galilean group. But that was not enough for these equations to be covariant. I mean, there were some weird relations going on, and we all had the experiments that initially got all the physicists and drove them mad. You know, that they were measuring the speed of light in different frames, and it all seemed the same. It was a very weird kind of phenomena going on when it came to relating observers and electromagnetism. So these we need to fix in a way that that recovers everything that we've done so far. So the obvious choice is an affine space that has one more dimension. And what I propose here is to consider a 4-dimensional affine space with no extra structure at this stage. So you just generalize or kind of upgrade your previous space, in which you had a 3-dimensional affine space, and you just promote it to a 4-dimensional affine space. But now you need to make use of your initial ingredients, which are free particles and light rays, and the way you arrange them is such that you somewhat recover all the dynamics or all the causality imposed with Maxwell's equations. And you all know that this is the light cone, or if you want to regard it more abstractly, it's just the intersection pattern of all free particles and light rays that indeed if you fix a point of space-time looks like a light cone in the usual diagrams. So we have this structure. So the starting point of my development is a affine space, 4-dimensional, with a cone. And a cone is just a topological cone. It's nothing to do with any set of coordinates, any set of quantities of real numbers. There's just topologically a cone. There's actually freedom to define, you know, as long as the section is convex, there's freedom to choose the shape of this cone. At this stage, just imagine that we have a cone in affine space. And of course, all the parallels are equally defined. So this is the starting point. So it's actually very intuitive, very nice to have it. Just think of 4-dimensional affine space with a cone and all the parallels. So we need to identify. We said that, well, of course, I didn't mention that you all know that light rays are the lines living on the cone and all the parallels. Free particles are the lines living inside the cone and all the parallels. So what is an observer in this setting? So we need to define something that can measure the positions or that can identify the things that our theory has. But our theory has only 2 ingredients. It's light and free particles, and we know that we're not made of light. So I mean observers. So we must be made of free particles, or in this approximation, which is just kinematic, we should be free particles. So the definition of observer, as you might recall from the useful expositions of presentation of special relativity, is just a set of all parallel lines to one free particle. So you know it's a congruence of parallel free particles. Now, what's the point of this? So far this is just some geometry drawing on a piece of paper. It's nothing more than that. So what is special relativity? What do we care about this theory? So the crucial point is that we need to measure time or the distance between things. That's what we do in physics at the end of the day. So we need to define a way in which an observer constructs a sequence of events on its own line, which is just a sequence of points, in a way that satisfies the universality condition that any observer could do the same. So let me put this more clearly. So we need a sequence of points on an observer that can be translated. I mean, we take one particular observer, one particular free particle, and we must construct a sequence of points in such a manner that when we translate that to another observer and make this the equivalent construction on that different observer, there is an obvious and unique way to compare both sequences. And so this is done in a very nice way. It's just geometric. You consider an observer that we call it the set of all possible parallel lines. So you take two arbitrary ones. So you are this line, and then you have any sort of parallel line that you choose. And then you basically construct the light cone at every single point. So the light cone here intersects just once with the future of this other line. You take that point, and then you construct the lectron there, and you get a single point in the future of this lectron, and so on. So you have a sequence of points, and you say, okay, very well, there's nothing special about that, because you can already, I mean, this is in a fine space, you can consider a vector here, and just multiply it with, integers, and then you get a sequence in the same way. That's true. But there's something special about this construction, and it is that it makes absolutely necessary that the principle of relativity is used. And this is why. So let me choose a unit on this line. So this is actually, maybe some of you may be familiar with the construction of R as a refinement of the rationals. So this is actually, you can reproduce a construction of the real numbers on this line. And then you take a unit, arbitrary unit. So your one of your real numbers is this quantity. And so you can compare any 2 points on this line with this unit, and then you get a real number out of it. So this is what we would call tau, and this is indeed the proper tau that we all know from special relativity. And it's a way to assign a real value from an origin that is fixed. And then we call this tau. Now what's interesting about this construction, and why am I concerned with all this fine geometry constructions? It's because if we have two observers and we make these two constructions on each of the lines. We have a time unit on each of the lines, and so we can actually compare them in such a way that we find a constant that depends on the pair of observers that makes it possible to compare any pair of proper times that are related with a light cone. So this might be a bit daunting, maybe abstract at this stage, but this is precisely what allows you to say that these two observers are equivalent. And so if you consider all the lines that are inside the cone, this relation imposes an equivalence relation in between observers. And that alpha U1, U2, if you carry on doing your developments, you will find in the end that the usual gamma factor between two observers is given by this. So you could regard alpha as a very geometric version of gamma, which is the algebraic version of Lorentz transformation in between observers. So this is, this object lives far more below in the development. So there's a long way to go until we get to actually being able to define this. But this is just a hint. So the possibility that you can do this, so the very fact that you can possibly do this, is precisely that we constructed each sequence of points on each line with light rays. If we did it arbitrarily with any two vectors, a vector on this line, a vector on that line, and you just have two arbitrary sequences, there's no possible way of comparing the values of the lengths of each separation of points in the sequence. Because this is an affine space and we don't have extra structure. There's no way of comparing lengths. There's no notion of the length of a vector in our affine space. So we need an extra structure to make it possible. And then our extra structure is the light cone. And making use of them, of all the light rays, we actually got that result. And this is precisely the principle of relativity by Einstein. So this is, we could not go further if we didn't impose this. This is an impossibility. This is not necessary. This is a possibility that you can choose. And it's only possible if you do this by means of light rays and with your fine construction. As I say, I'm omitting all the details, and it's not completely straightforward because these are four-dimensional cones, and you have to think carefully what the intersection pattern is. It's not valid to just draw a two-dimensional diagram. Now, when we have this construction, it's actually straightforward to start defining the usual notions in special relativity. It's straightforward to say, okay, I have the ability to tell what the time separation of two events on a free observer is, on an inertial observer, and so any parallel, you can just argue that these two are the same because they were constructed with parallels. And so effectively, if you take an origin, you could assign an arbitrary point, say A, a value that you call t. It's obviously subject to u and the origin, so you may want to make that explicit. But you have a function that is linear in A when you regard it as vectors, and that gives you the coordinate time of every point in the space. So basically, if you define the kernel of this map to be your simultaneity space, you have a three-dimensional submanifold, which is an affine manifold, it's just a plane of three-dimensional space, three-dimensional affine space. And you can prove that by defining the distance in the natural way, in which you assign the distance between two simultaneous boundaries, we define it already like that. You just construct your light cone there, so you have a light cone, and then you have two intersections here. So you basically take the distance to be, which you want to be this straight line here, to be this amount tau that we already constructed, times some constant, some arbitrary real number, some arbitrary real number. And I call this C just for convenience, because in the end we'll see that light rays have a 3 velocity that is precisely this number. But that's just a result. We didn't use the light speed or anything. Now, we want to reconstruct Minkowski metric. So with this construction, we see that we can assign a real number to any point on a timeline curve or line, and then any 2 points of the simultaneity subspace will actually be able. I mean, you can assign the distance between them, and this is mathematically a distance. So it's got all the properties of a distance. So and so you can argue that there's a natural scalar product, which is Euclidean scalar product on every single simultaneous space. And so, if you're given a vector that leads from some free particle, the kernel of this time coordinate, or if you want, the complementary space, is indeed a three-dimensional affine space, and you have an inner product defined in that space. So, effectively, we have vectors belonging to this space, vectors belonging to this, and we have vectors belonging to the cos. So we have 3 distinct types of vectors, and for each of them, we will, by hand, define them to have this value. So the primary one is this one. We want the Euclidean metric to be recovered in the 3-dimensional subspaces. And so we define it like this. We define the distance that we already saw that we have there squared for some v that comes from a couple of points A to B. Then for any null vector, for any vector on the cone, we define it to be 0. And for any vector living on a free particle, we define it to be minus c squared. It could be minus 1 with your choice of units. And now that's only the squares, but the Minkowski metric is to be symmetric, so we can use this nice formula, which is just an identity for symmetric quadratic forms. And then if we have the squares, we have indeed any possible pair of values. And so if you choose a basis that has a unit vector here, or c squared length vector here, and since you have here an Euclidean 3 space, you choose just an orthonormal base there, that is precisely a Minkowski base of your space, and the metric, and this map has a metric expression on that basis that reproduces -1, 1, 1, 1. So we've come to the conclusion that it's possible to recover Minkowski metric just from the initial light cone on a 4-dimensional affine space. So I just wanted to show you that this is possible. I didn't show you the details, but this is possible. It is possible to recover the Minkowski metric from a light cone on space-time. And I mean, this is something like, well, this is obvious. It should be the case. But the interesting point is that by doing this, you realize that it is only actually necessarily possible if you impose the principle of relativity and if you impose the arrow of time. So you have to quotient with these 2 equivalence relations. You have to quotient for observers pointing towards one of the parts of the cone. It really doesn't matter which one, but just one, and stick to that. And then you have to impose the equivalence relation between observers that can translate the units. So you have this alpha factor, and so they will translate into the gamma factor, the transforms when we consider Lorentz transformation, which is a long way in the development. So I hope this shows the taste of this sort of consideration. Just from careful developments, careful mathematical developments, we can actually derive Minkowski-metric. And so we basically went around and said, okay, so it is good to use Minkowski-metric. So now some further considerations. So recall that we defined inertial observer as a congruence of parallels. And if we think about a finite space, it is infinite in a sense. So it goes in all directions, in all directions, open. So there's no limit. So in some sense, we'll be very naive to think, okay, this is the universe, this is the whole space. Because why? I mean, why? We started from considering Maxwell's equations and the interaction between particles and light rays, but that's something that you can measure on a laboratory, on a local setting. You don't go and make statements about things moving in a galaxy far away or in the sun. You make statements about things that happen in a room and you can measure with straight rudders and this sort of stuff. So it was very naive to think that the initial finite space that we considered, the four-dimensional finite space that we considered, was actually all the universe. So with this perspective, general relativity is actually very natural. It's very, very straightforward to think, okay, let me just assume that this happens locally. So we have that restriction. I mean, all these discussions should happen locally, but the global issues of my space-time are left free. So now, this is precisely the equivalence principle, and it's another nice feature of this development, that you see clearly that you need this if you want to make sense that your observers were defined as congruence of parallel lines, and they were, by definition, ubiquitous to the whole universe. And that doesn't make any sense. I mean, we are just, small place, being able to do and perform calculations and sort of measurements in a small place. And there's no any kind of sense in having observers that cover the whole universe, which is the case in Minkowski discussion. In Minkowski space setting, we have observers that cover the whole space. And then we have the same issue that we should translate the time unit between two different observers. And so, again, since we have the relativity principle and equivalence principle put together, we have the notion of two overlapping special relativities that not exactly the same, but just overlapping. We'll have some kind of consideration of how you move time units smoothly from one observer to the other. And so you can start noticing that the hidden structures that we will get mathematically are, of course, the one from the first equivalence principle is that you have a smooth Lorentz metric. So effectively, at every single point, you have a tangent space, which is locally isomorphic homomorphic to your open set and your manifold. And from the transportation of the time unit, you get the smooth Levi-Civita connection. And so, of course, this is very sketchy, and I mean, it would be very heavy to develop all the details. I didn't do it myself. I did for special relativity, not for this general setting. But you can see the pattern. I mean, you can see that just by relaxing the conditions of being globally such, I mean, of being globally an observer in the whole space, just by relaxing that, the natural sort of theory that you get is general relativity. And so now I just want to say a couple of things of the sort of ideas that came to my mind when I finished dealing with these developments. And they might be completely naive and useless, but I just want to share them with you so that you can comment on them. So the basic questions that arise, I mean, in my opinion, are what is the underlying structure of all this? So I started from some abstract consideration of what free particles and light rays were. And by realizing them in a nice way, in a finite space, I consider it common. And then I put them together in a way that is geometric, that I can visualize, I can compute. And then I got special relativity. And then I relaxed a little bit the assumptions, and I got general relativity. And so this is, to me, this raises the question, so what is causality? So causality was something that was behind all this. So it was, in the first place, was causality, and then if you realize your theories in specific spaces, taking straight lines on a fine dimension, on a four-dimensional fine space, or if you take geodesics on a Riemannian or Lorentzian manifold, you get the constructions that you already know. So to me, this is pointing towards a structure that is underlying these theories. So there's some sort of general common structure between these developments. And maybe if we had a general set theoretic description of the particles and light rays, and basically take a light cone and by inspection get all the patterns, all the intersection patterns between free particles and light rays, and formulate that entirely in terms of sets and intersections of sets. Maybe we could have the minimal causality requirements for any physical theory to satisfy. And this is just as I say that if you have an arbitrary physical theory in which you can identify clearly what a free particle and what a light ray is, regardless of the nature of these objects. So, for instance, if you're thinking of string theory, maybe there are world sheets instead of lines or things like that. Maybe if you do this successfully, maybe you have a template in which you can actually see, okay, does this fit to the causality that is required for recovering special relativity and general relativity? So, I don't know, this is just a very relative, I really do not think like that. And so it may be useful to have that general framework just to consider further physical theories. It is just starting out. So thank you very much.
Okay, what question do we have for Carlos?
Yes. I didn't quite understand. You, in the part where you just put the norm of the timeline vector to be
Yes.
minus c squared,
Yes.
that was like under which argument? What was the argument to choose? Because that seemed to me like saying this is the metric. Like, didn't seem to me natural.
So this kind of, the V in the first argument there is a vector.
No, yeah, but why minus 1?
Well, it's just, you just impose a negative number.
But that is like basically the same that saying the metric for this space is the Minkowski metric.
No, wait, but I mean, the thing that you have previously defined is this object, so the metric for the 3 space. And then from definition of distance, you actually, it is necessary that the way you define distance is with a line that is generated with u. And I'm going to say that's a unitary time-like vector, even though we don't have that notion yet, just the name. Then, if that u is used for the definition of distance, then for the structure I mean, if you use the structure in which you construct the distance, the value of this length is actually just the distance divided by c squared. So if you want to make sense of the, of the structure that you used already, you need that number there. If that is to be the norm of this vector, because that thing should be the norm of this vector. So it's just a distance squared restricted to the one-dimensional subspace instead of the three-dimensional subspace, right? And so basically you could see that it's negative because it's the same question: why it should be 0 for the light cone? So any vector from the light cone can be expressed something spatial and time, space light and time. So if you have the same value for the two of them, they must have opposite sign for it to cancel. Right? So it's basically, this choice is basically the geometry of the cone taking place. But the crucial point is not how, because this is just actually tuning your object such that in the end it's the precise Minkowski metric. If you say instead of -1 you say -2, it doesn't make sense. But so this is actually just you know that you want to get to Minkowski metric. It's not that you deduce Minkowski metric in the precise definition that we use normally in physics necessarily, but it is possible. You know that there exists such a map. And of course, there's a class of maps that they all have some arbitrariness in the definition, but you can make the choice that you record it precisely in Minkowski metric. I mean, obviously, if you multiply the arguments in Minkowski metric, you make changes. I mean, you recover the same kind of physics.
Probably
Yes.
I skipped some passages, but I don't quite get how do you justify the pseudo-Riemannian fact. But it seems to me that you're just shifting the problem of, I mean, at least to me, what seems not natural in the Minkowski metric is that it's pseudo-Riemannian and not Riemannian metric.
Yes.
So you're shifting this problem to saying there are cones.
Well,
How do you justify the fact that there is a -1, or there is a a negative eigenvalue in the metric?
in the metric. So again, that's a choice for, you want to, what you have in mind is to construct a bilinear form such that when you restrict it to vectors pointing in the direction of some free particle or vectors in the three-dimensional subspace, then you recover the values that you already defined as the proper time and the distance, which just come from the geometry of the space and the construction of the geometric clock on every single timeline line. But you have certainly you have a one-dimensional distance in one direction and three-dimensional distance in the three complementary directions. So you have two, and those are two separate sets with the same kind of structure, with the Euclidean structure, or in the general manifold setting, the Riemannian structure. So you have, and there are two distant, and you cannot go from one to another, precisely because the way you define the values is with the column. I mean, that's a bit of shift in perspective. The way you actually compute the values of this distance of this time is using the column structure. So you cannot make one to the other. So if the two were Riemannian, that means that it would be meaningful to speak about distances in between light rays, but that's impossible. I mean, you cannot construct a clock on a light ray from the definition. I mean, you cannot construct a geometric clock the way I did, with this kind of ladder of light rays on a light ray. It's geometrically impossible. So that's precisely why you have two distinct spaces, and the minus sign, and the reason that, there's arbitrariness in where you put the minus sign. You just need to have opposite signs. If you want to find a bilinear form to, make sense of all this in a compact way, so it's a very constructivist perspective. You just take all your facts and you put them together. But the initial fact that you actually have in mind is that you have two distinct Euclidean spaces. One is time. That's an Euclidean. Time restricted to one of the lines. That's an Euclidean space, one-dimensional Euclidean space. And you have three-dimensional simultaneity space of that line, and that's a three-dimensional Euclidean space. But those two don't talk to each other. They're separate by a cone on which you cannot define a distance. It's impossible to define a distance, or you want just assign 0 to every pair of points of that space. So it's a bit of a shift in perspective. You have to think that the values of the proper time and the distance are geometrically evaluated in the sense of actually, drawing the light rays and counting, if you like. So that's why I said in the beginning that you actually construct a real line with this procedure. Even though we said this was a four-dimensional affine space, and of course you have the real line already constructed over every line because it's by definition an affine space. But you have just to regard it like this, a geometric R constructed in this way, with this level. So that's why, the minus sign is not important in the sense that there's one minus sign, three minus signs. That's not important. The important is that they are opposite. And you have some non-empty set of vectors that must be 0. And that abstraction is basically coming from the fact that you define the values of those distances from the light couple. Yes?
Can you say a little bit more about the constraints on and the consequences of the shape of these diphones?
Oh yes, sure.
Yeah.
So I was thinking about this a bit before the talk, and the basic idea of the four-dimensional cone is, I mean, if you imagine it, it's like a sphere expanding in 3D. So if you, I mean, obviously, if you have something like, you know, like a potato expanding and it's an arbitrary form expanding, it's not exactly the same. But you have some freedom, and as long as the thing and the shell that is expanding in 3D is convex, it's enough. So because you want to sort of, you have this, you want that two lines, that a line goes like that. I mean, if you have some kind of curvature like that, you can intersect more times, and that's not acceptable for, I mean, for the constructions. But there is some kind of, I mean, if you have something like this, still possible. It's not, so the key message that you should retain for this is, it's not very important as long as you can do such a thing. It's not important if it's, you know, straight or it's curved in a way that it's still possible to do it. But I guess the constraints are basically the shape of the shell that you should imagine expanding in 3D. That should represent the section of the body.
Okay, let's thanks Carlos again.
Thank you.
Next speaker.
Outside.
He's just
Wait.
Hi.